So hello again, here we are. Oh, let's put the data in place where we finished in the last video. Yep. So we first came to the conclusion that we need to perform multi-level analysis when analyzing performance, which is an individual level outcome. And oh yeah, just to be sure, multi-level regression analysis is always focused on an outcome on the lowest level. Okay. So what we are going to do, we are going to try to predict the variance on both levels by adding predictor terms. So I will first concentrate on individual level predictors. So in this case, this is workload or work pressure. Now let's first focus on ground mean centering. Ground mean centering means that you want to center your variables to a mean of 0 for the whole sample. Okay. And autonomy. Autonomy, second variable on the lowest level. Ground mean centering again. You can also use uncentered scores, but especially when you want to calculate interaction effects, and we will do that later on, then it is wise to center your scores because you avoid multicollinearity. But that will not be covered in this course actually. So now we have two variables that are measured on the lowest level, and we have to run the model again, so we press start. So we see that something changed. So let's go to Excel and add these values, right? So we have now, I set up here first model, model 1. And we can compare this model actually to the null model. We will come to that. So work pressure, I will call it, okay? So the higher the score, the higher the workload or the work pressure employees feel. Autonomy. Autonomy also, the higher the autonomy, the more freedom employees have to perform their duties the way they want to perform it, right? And we also have a constant. So the constant is 3.5952, comma 3,952. Again, let's see, for the whole spreadsheet we want, we want, nope, we want, come on. God. Excel. So it's also big. I think if I include words, then it doesn't work. Okay. Yep, here we go. And the standard error is 0.033. And the Z value is significant, but okay, this is not a predictor, of course. For work pressure, we have a value of, this is an unstandardized estimate of 178,051. And for work pressure, we have 0.058 and 0.036. And of course, we can just divide the unstandardized estimate by the standard error, and we get the Z value or the T value. And this is actually higher than 1.96. So we have a significant effect of work pressure, right? This is lower, so we do not have a significant effect of autonomy. Well, actually, you can also look at the p-value, or calculate the p-value. You can look at the table first. But you can also calculate the p-value using MlwiN. And you can go to data manipulation, command interface, and you say normal probability. And then you enter the z-value, 3.490, right? Enter. Then you go to output. You see here, significant predictor. The p-value is below 0.05, so I would say lower than 0.001, for instance. Yeah? Oh, yeah, that one too. But we are not so interested in that one. And the other, 1.611. NPRO, oh, what's this? NPRO 1.61 is almost significant. But oh yeah, you have to take care here that he has, I think, the two-tail test. So you have to multiply the p-value times 2. Because, yeah, it depends on your model, of course. But I would say autonomy you would expect autonomy to positively predict performance, and then you have actually a hypothesis in a particular direction, right? And then you should always multiply the p-value by times 2. So this 2 times, 1, 5. If this would be hypothesis 1, okay? So, why is this there? Oh yeah, he doesn't recognize this as a value. Okay, so we just enter 001, okay? Okay, going to the variance of this model. Then I think, oh, no, I clicked it. Model equations. Here it is again. So now we can look at the variance that is unexplained after adding these variables. So 0.125, oh, comma, and comma 214. Total deviance. No, it's not necessary actually. And then we have the deviance of 744.996. Oh, comma. It's getting late. 996. Okay, and we could also say, yeah, let's delete that. That one was the. This one was the one-level model actually. We delete it. Okay. So I would say the chi-square difference is. You can also calculate that. So the null model was 759. Now we have some predictors in the model, and the chi-square went down by 14.655, right? So let's go on with this. So it's 14.655, and we added 2 variables on the individual level. So the first thing you want to know is, or one of the things you want to know is whether or not this model fits the data better as compared to the null model. Or actually, yeah, that's what you want to see. So 14.655 is just a chi-square test with 2 degrees of freedom because we added 2 variables. Would be, so we can go to data manipulation, command interface. I also put an online calculator, chi-square difference calculator on OASE, but you can also do it here. 14.655 with 2 degrees of freedom. Help. Of course, CPRO 14.655 with 2 degrees of freedom. You enter this, you get output, and you see here the chi-square difference is significant. It's below 0.05. 0.0006. Okay, so let's say 001, okay? So now one final thing we can do is also to look at the variance, the explained variance. Now remember, these variances are actually variances that are unexplained. Make it complicated. So we started out with a null model which had an unexplained variance of 0.139 on the team level. And we now have some remaining unexplained variance of 0.125. So, of course, oh, this is already percentage. We should not do that cell number. Oh, this is not correct. So, here you see that we have, is it correct? So 0.9, 25, 0.1, yeah. So this would be the amount of variance on the team level that we have explained, not so much. And then, of course, we have also percentage. So I hope you see what I'm doing here. Let's see. Okay. So we see here that unexplained variance here is 0.139, 0.125, so the explained variance is 0.014. Here the difference in unexplained variance is 0.001. But if you want to calculate this amount of variance as part of, like, I would say I prefer the total variance explained. So if you look at the grand scheme of things, you say, okay, I want to divide it by the total variance that is in my model. And let's do this also, because so the explained variance divided by the total variance, then we can take the percentage. Oh, so not so much variance explained, right? So as compared to the total amount of variance, we explain 4% on the team level with this model and 0.3% on the individual level, which is kind of interesting because it shows that on the team level, well, you can be cynical and say this is not a lot of variance explained. That's right. But when still looking at these two variables, then you see that most of the variance is explained on the team level. So that means actually that we work pressure and autonomy on the between team level. The differences between the teams in work pressure and autonomy, they predict individual performance and not so much the variance that lies on an individual level, so individuals within the team. So it is interesting to see that because it has different meanings. I hope you see that. So, okay. Of course, you can also calculate the variance as part of only the team level total variance or the individual level variance. But I leave it here. So we have two variables, work pressure and autonomy. And you see here that they are, you predict something of the variance, but not a lot. Okay, let's move on to the next video where I will add team level or group level variables. Okay.